It's my pleasure to welcome here to SDSU Professor Rajesh Rajamani from the University of Minnesota as part of our TILOS-SDSU collaboration second seminar we're hosting. Professor Rajamani obtained his master's and PhD degrees from Berkeley and his BTech degree from IIT Madras. He has been part of the faculty in mechanical engineering at University of Minnesota since 1998 and is currently the Benjamin Y.H. Liu TSI Endowed Chair Professor. He also is the Associate Director of the Minnesota Robotics Institute. He's currently interested in estimation, sensing, and control for smart and autonomous systems. He's been co-author of over 190 journal papers, co-inventor of over 20 patents. He's an IEEE Fellow, ASME Fellow, has been a previous career award winner at the NSF, Hugo Schuck Award winner, Ralph Titor Award from the SAE, and Charles Stark Draper Award from ASME. Plenty, I think, of accolades over his nice career. And he has also spun off some of his projects and devices commercially through startups. So yeah, join me in welcoming Professor Rajamani.
Thank you so much, Brian. Thank you so much for the invitation and for the opportunity to present this talk. So the title of my talk is Challenging Estimation Problems in Vehicle Autonomy.
Minor, let's do this. Okay, it works now.
Yeah. Okay. Okay. So the outline of my talk is as follows. I'm going to just get rid of this a little bit. Hide video panel. Yeah. Okay.
Also, the next one, high floating lead controls. Yes. Okay.
Okay.
Nice.
Okay. Yeah. So all the technical problems I hope are solved now. So I'll talk about nonlinear observers for estimation of non-measured variables. Just a little bit about that. And then I'll mostly talk about interesting applications in transportation involving estimation. So I'll talk about teleoperation of an autonomous vehicle. I'll talk about protection of vulnerable road users like bicyclists and e-scooter riders. I'll talk about magnetic position estimation, finding the end effector position on off-road vehicles, and I'll talk about some smart road infrastructure. Okay, so various applications of estimation. Yeah, it seems to.
I think if you use the mouse to click the slide once, it should.
Okay.
Now, hopefully it's run.
Okay. So MindLab does a lot of work on nonlinear observers. And what are nonlinear observers? Basically, they're used to estimate variables that we cannot directly measure. Okay. So we typically, so in a nonlinear observer, what you do is you have a dynamic model of the system and combine the dynamic model with some measurements to estimate all the variables that you're not able to measure. Okay. So some examples of estimation algorithms observers are as follows. Use of an inertial measurement sensor in GPS to estimate variables such as slip angle and tire road friction coefficient. So slip angle on a vehicle is a very important variable. Is basically the angle of the velocity vector with respect to the direction of the vehicle. It's an important variable that you need to know because it tells you how the position of the vehicle is evolving, okay? But it's not a variable that you can measure. Likewise, tire road friction coefficient. So that's going to tell you how slippery the road is, okay? And that again is a variable that you cannot actually measure with regular inexpensive sensors. So what you do with estimation algorithms is you estimate these kinds of variables, okay? You combine dynamic models together with well-designed algorithms and you estimate these variables. So those are called nonlinear observers, for example, right? So we do a lot of work on design of algorithms for nonlinear observers. The dynamic systems we handle are often nonlinear, and so that's why we need, nonlinear observers. Instead of linearization based methods, we use the original nonlinear dynamic model. We use Lyapunov analysis. We use nonlinear observers that give you guaranteed conversions of the estimates to the actual variables. So we do a lot of work in this area. And, we normally, we publish theoretical papers primarily on observers for nonlinear systems. So these are some examples of theoretical papers that we've published in the last few years, So we published in the Automatica, in IEEE transactions on automatic control, IJRNC, and so on. So all the theoretical work we do is on this topic, observer design for nonlinear systems, and we publish those kinds of papers. But this talk is really not going to talk about these theoretical results, okay? So as far as today's talk is concerned, we're just going to see how estimation is used in some very interesting applications, okay? And how it enables some novel applications. That's what it's used for, okay? Okay. It seems like my pointer is working now. So the first topic I'm going to talk about is teleoperation of autonomous vehicles, okay? Okay. So what is the motivation behind teleoperation of an autonomous vehicle? So basically we say that autonomous cars need occasional human intervention and teleoperation. So, typically when you're testing an autonomous vehicle, there is a safety driver in the car, right? And if something goes wrong with the autonomous vehicle, the safety driver takes over. But you need teleoperation if you want to scale up the deployment of autonomous vehicles, right? So otherwise you're going to need a safety driver in every vehicle, in every autonomous vehicle on the road. So that is one of the motivations for having teleoperation. Teleoperation is used actually widely in a bunch of applications in the real world. So I don't know if your campus has food delivery using robots, but our campus does, and that is entirely teleoperated. Okay, so basically you can order food, and the robot will come to the door of your building, and then you enter the code inside the robot, and then you take your food, right? So that is a teleoperated application. Now. So that's a widely used teleoperation application. There are also some teleoperation applications of autonomous vehicles, of vehicles, full-scale vehicles. So there is a company called Halo in Las Vegas, which uses human teleoperators to remotely drive rental cars to locations where the human customer needs them. So basically, you need a rental car, they will teleoperate and drive the car to you, and then you drive the car. It's your car after that, right? You're renting it. And then when you're finished with using the car, they will teleoperate and take the car back again. So this is in a limited geographical domain in Las Vegas, but it is a real world application that exists. So teleoperation is being used. So what we feel is that autonomous operation accompanied by occasional teleoperation or operator intervention is going to be a very valuable technology in the future. Okay. Now, what I'm going to talk about today is one aspect of teleoperation called predictive display. So for teleoperation, what you need to do is you need to transmit a lot of camera images from the remote vehicle to the teleoperator station so that you can create, the environment of the vehicle for the teleoperator, right? So the teleoperator needs to see what is the environment around the remote vehicle so that he or she can drive the vehicle remotely, right? So you need to recreate that. Now, the challenge with recreating the remote vehicle environment is that camera images are bulky, it's a lot of data and you need to transmit that by using wireless networks. You might not have 5G everywhere, and even with 5G, it's very difficult to actually transmit camera images sufficiently fast. So what happens is you end up getting a lot of variable latency. So in other words, the camera images arrive after quite a bit of delay, right? So what we have found that if there is a delay of even 170 milliseconds or more, then it starts becoming quite difficult for the teleoperator to drive the car. Okay. So what the technology that we are working on is called predictive display. What we do is we take the old camera images, the ones that are delayed. We use observers to estimate, the positions and orientations of the ego vehicle and of the nearby vehicles. And then, we use that information to update the camera images. So we take the old camera images and from them we create new camera images and we do intermediate updates of the display for the teleoperator. And by doing that, we can actually help the teleoperator to drive in spite of, the delay in receiving camera images. So that is called predictive display. Okay. So this is a photograph of the teleoperation station we have in my lab. Is basically a big monitor and a powerful computer. This is a steering wheel. Then we have throttle, brake, actuators, and there's two types of studies that we've done so far on teleoperation. We have done human in the loop simulation studies. So we use we have simulation software here, and so what the human subject does is controls one of the vehicles in the simulation. So we do human subject studies using simulations, and then we also have an autonomous vehicle, and so we want to do experimental studies using our autonomous vehicle for teleoperation. Okay. So let me tell you a little bit about one of the aspects of teleoperation that we have addressed. It is about how to do one of the things we discovered while trying to track trajectories of nearby vehicles. So basically, what we need to do is for the remote vehicle, right? We need to track the trajectories of all the nearby vehicles, okay? Because we need to use that information for updating the display, right? So, so what has happened in the past is that target vehicles are tracked by using estimation algorithm, but they are often modeled by very simplistic dynamic models. So, for example, the model might say that each vehicle has decoupled lateral and longitudinal motion, and lateral acceleration is equal to 0, longitudinal acceleration is equal to 0. So those kinds of simple models are typically used, or the kinematic model is used. So in this kinematic model, the states are position, velocity, and acceleration, and orientation and slip angle, and then you have some kinematic equations. It turns out that this type of model is good for inertial position and inertial trajectory variables of the vehicle, but it's not good for relative variables. So because the radar on your car is a moving car, so your car is going to have rotational motion, accelerations, and so on. So the radar is mounted on your car, and then you are measuring the distance to another car with it. So because it's a relative measurement instead of an inertial measurement, it turns out that this model is going to give you errors, and it doesn't work all that well. So this is an example to show you that the old motion model is incorrect, right? So if you misuse inertial motion model for relative motion, you have errors. So when the ego vehicle is doing a lane change, the relative position is incorrectly estimated, and both in the longitudinal and the lateral position point of view. So that's why we need to use correct models. We cannot misuse inertial motion models for relative motion. So what we have done, is we have found the right kind of model to use basically. So what we do is we write down the inertial dynamics of each of the vehicles, the ego vehicle and the target vehicle. We write down the inertial dynamics of each, and we define state variables, which are the relative motion variables, and we find the dynamics of the relative motion variables correctly. And this is the type of model we get. Okay, so this model has 6 states. The states are lateral and longitudinal relative distances. And then we have velocity, acceleration, orientation, and slip angle of the target vehicle. So it's a combination of relative variables and variables related to the target vehicle. Okay, so those are the states. And then we have nonlinear dynamics, as you can see here. The inputs to this model are, we assume that the velocity of the ego vehicle and the slip angle of the ego vehicle are known. Okay, so these are variables that we need to estimate as well. So this nonlinear model together with nonlinear observer design is what we use for estimation of trajectory variables of each tracked target vehicle. Okay. So now what I'm going to show you is, so we use these algorithms for estimating. We estimate the ego vehicle position and orientation. We estimate the nearby vehicles position and orientation. So we use that for predictive display. So the human subject studies that we have done with the simulation model. So there are going to be 5 human subjects. They're going to drive on this route that you see over here. So some parts of the route are pretty curvy. So so the driver has to really pay attention and drive properly in order to stay on the road and not leave the lane. Okay. This is what the simulation model looks like. Okay. In this particular case, we have 4 lanes here, 2 in each direction. This is what the teleoperation station. This is what it looks like. So you are basically sitting here, and you are, you can. It is very similar to how a real car would be, right? So you are going to see the road through this car, and you're going to do teleoperation. The speed of your car is displayed over here, okay, and you can see the lane lines and so on. Okay. So we assume that there is no latency in sending steering wheel, throttle, and brake commands from the teleoperator to the vehicle due to low data size. So these are variables that have very small data size. So there is no latency in sending your throttle commands and your brake commands and so on. But there is a lot of latency in receiving the camera images. Okay. So this video basically shows you what happens when there is a 0.5 second delay. So I told you earlier that if you have even a 170 millisecond time delay, it starts becoming difficult. This video is going to be with half a second of time delay. So with half a second, it is very difficult for the teleoperator to do that, almost impossible. Okay. So let's look at this video here. So the teleoperator is trying to drive and stay on the road, and he's not able to do a very good job. You can see here that the car keeps leaving the lane, he's going outside the lane, right? So this is because of the half a second delay. Okay, it's pretty difficult to drive with the half a second delay. Okay. And not only that, there is intensive effort needed for the teleoperator as well because of the time delay, right? You have to really be paying a lot of attention and trying very hard. So this makes the driving task very difficult. And in spite of the driving task being very difficult and requiring a lot of effort from you, in spite of that, you keep going out of the lane. Pretty difficult task, okay? Now, on the other hand, with our predictive display system, you'll see in this video, that the driver is able to stay in the lane. It becomes much easier to drive. Also, the driver is actually able to use much higher speeds. It's actually able to go at higher speeds, stay in the lane, so the driving task really does become much easier, okay? So this is driving with the predictive display, and unlike what you saw in the previous video, right? Here, the driver is able to stay in the lane, right? Is not really going out of the lane at all here, right? So this is what predictive display is useful for. So if you look at our data with the 5 human participants, so each human participant was driving for 10 minutes in each of 3 scenarios. So the 3 scenarios were without any time delay, with the half a second time delay, and then with the predictive display, right? So first, he or she drives without any time delay, so that they get used to using the simulator, right? And then with the half a second time delay, and with predictive display. And what you can see here is when there's a half a second time delay, the driver goes out of the lane many times. So, approximately 11 times out of the lane. Okay. On the other hand, the predictive display, the performance is as good as that of the system without any time delay. Okay. So the user hardly goes out of the lane. Furthermore, the excursion outside the lane can be very big when you have a big time delay. So this is an example from one of the human subjects, and you can see that not only, so this is the lateral distance, and you can see that the edge of the car is going outside the lane. Not only is it going outside the lane, it has a pretty large excursion, like 2 meters of excursion outside the lane, right? So huge excursion outside the lane. On the other hand, with the predictive display system, the car is entirely inside the lane for this particular example. Okay. So that is work using the simulator and human subjects, right? Now, what we want to do next is actually use this on a real autonomous vehicle, right? So this was a simulation study, even though we used human subjects for experimental inputs, but it was a simulation study. But now what we want to do is we want to use this with an autonomous vehicle. Okay, so what we are doing for that is developing this predictive display system, right? So that you can use real camera images, yeah, and okay, so what we do in this predictive display system, right, is we use a combination of LiDAR and camera images. Okay, so what we do is we take the LiDAR point cloud, we project it onto the image. So we find, we project the LiDAR points onto the camera image. We find all the pixels on the camera image which have the LiDAR points, and then so we know the distances to those points, right? Then what we do is we do state estimation. So for the ego vehicle, we find the new position and the new orientation of the ego vehicle, right? So, so in other words, if you have a camera image and if you know the distances to all the pixels on the image, right? And if you know that the ego vehicle has moved, this much, and this is its new orientation, then what you can do is you can take the old camera pixels and you can transform them to create the new camera pixel, right? So then you get the refreshed or updated camera image. So that's what you can do. So that's what we do. We do the state estimation. We transform the camera pixels, right? And we create new pixels. But there is one more thing we need to do because the LiDAR points are not that dense. Okay, so they're not going to give you all the pixels in the image, right? So you're going to get some points on the image from the LiDAR, but not all the pixels are covered by it. So then what we do is we use interpolation and extrapolation. So for example, right, some part of the image is going to be the sky, some part of the camera image. Okay, obviously the LiDAR is not measuring the distance to the sky. You're not going to get any camera, you're not going to get any projected points on the sky, right? So So what you do is, you do interpolation and extrapolation, okay, and for that we use polynomials. And so this is called the vector field method, so that's what we do. So some camera pixels we find directly from the transformation, the other camera pixels we find by interpolation and extrapolation. So that's how we get the updated camera image. So what I'm going to show you in the next slide is the video of this. So here you can see, this is the ground truth, okay? And if you compare the delayed image and the ground truth, you can see that the delayed image is behind the ground truth, right? You can let's play it again, okay? So I know there's a lot going on here, but you can if you look at it carefully, you can see that the ground truth is ahead of the delayed. The delayed is got a 0.5 second delay, okay? And then if you compare the vector field and the delayed image, right? So it started playing again. You can see here, the vector field is actually pretty close to the ground truth. Okay, you can compare these two here. Okay, so essentially we are able to create the ground truth from the delayed image by using state estimation and transformation. Okay, so this is what we are doing. This is the predictive display system that we are using. Okay. And here's some static images to show you the difference. Okay, so this is the ground truth, and if you look at the delayed camera image, you can see that the delayed camera image is behind, right? It's not able to see these cars here, right? Those are not visible. These cars are not visible because this is the delayed image. The vector field image, on the other hand, has those vehicles, right? So here what we are doing, I mean, one of the things I didn't mention is we also do merging of cameras. We have a center camera, we have side cameras. So we merge the cameras as well. So when you're turning, so if you don't use the side cameras, when you're turning, you get, otherwise you have some portion of the image that you cannot see. Okay. So so this is one of the projects that we are working on in our lab, basically predictive display for teleoperation. Okay. So our conclusions from this project are, from what I've shown you so far, are that significantly more intensive human effort is needed for driving in the presence of display delays. It is important to use the correct dynamic models for tracking nearby vehicles correctly. The use of predictive display increases the ease of driving, decreases the number of times the vehicle goes out of the lane, and also decreases off-center excursion distance. Okay. So future experimental work on teleoperation will be done using the MinCab vehicle, which I'm going to show you next on the next slides. So we have a NSF size large project that got funded about 1 year ago. So initially we were working with some seed funding from inside the university, but then we got funded last year with the NSF size large. So the PI of the project is actually from computer science, and I'm one of the co-PIs. And this is the title of the project. Yeah.
Yes, a quick question. So for the predictive display, I wonder if just moving the pixel values to new locations sometimes creates some artifacts like blur or maybe like lighting problems. And so recently in computer vision, there's this Gaussian splatting method that has been quite popular. We represent the 3D scene with Gaussians and project those to the image for rendering.
Yeah.
I wonder if there are pros and cons. I imagine the Gaussian splatting will probably be slower than what you're doing now, which is something we don't want. But on the other hand, might look visually a bit better than copying pixel values depending on the delay amount. So I'm curious if you have.
Yeah.
Pros and
Yeah.
cons.
So definitely, when you use interpolation, right, we get warping. Because you have pixels that are correctly transformed, and then the others are all you're transforming them using interpolation. So you can get quite a bit of warping. And so you can come up with some techniques for using the warping, but that is one of the problems that we have, with what we are doing right now. And Gaussian splatting, yeah, we've considered that as well, and that is one of the things we want to work on as well. So Gaussian splatting, for example, it helps you do things like merging of multiple cameras together and so on. Those kinds of things become kind of inherently, they're all inherently built in when you do Gaussian splatting. And yeah, that is a good technique to consider.
Thank you.
Yeah. So I mean, the key from our point of view, one of the key technologies that is enabling this work here is the estimation. So doing estimation of the ego vehicle's position, orientation of all the nearby vehicles. So that part is critically needed, irrespective of what method you use here.
Yeah.
Okay. Sorry, I'm going in the reverse direction. Okay. Okay, so this is the autonomous vehicle we have at the University of Minnesota. It's called the MinCab vehicle. And it's basically a full-scale Chrysler Pacifica minivan. It was set up by a vendor called Data Speed, which is a pretty well-known vendor. And what they did is they instrumented the vehicle with a whole bunch of sensors. So the sensors on the vehicle are, there are 3 LiDARs, there are 3 Ouster LiDARs. There's a dual antenna GNSS system. There is a whole set of cameras. There's a forward-looking radar, backward, rear-facing radar, IMUs, lots of sensors. Then they set up ROS-based software for vehicle control. So they wired all the sensors to computers and set up ROS-based software. And they have done some of the low-level work on the vehicle, like trying to enable the vehicle to follow a desired acceleration, enabling the steering angle to follow a desired steering angle. So they've implemented some of these things. And then what my lab has done is we've actually implemented some of the autonomous driving functions on this vehicle here. Okay. So we have a couple of projects using this autonomous vehicle in my lab. One of the projects is on steering control on unpaved gravel roads using GNSS, okay? And so this is a project funded by MnDOT. And then we also have a different project on cooperative driving through rural intersections using communications from the intersection, okay? So this is funded by a UTC. UTC is a University Transportation Center. So these are the 2 projects on the autonomous vehicle that we are working on, okay? So let me give you the motivation for, why we want to drive using GNSS, right? So what happens, first of all, is that in states like Minnesota where you get snow, snow can stay on the lane lines much longer than it actually stays inside the lane. So if you look at this road here, the lane lines are all covered with snow. But for a human driver, the human driver can actually see where the lane is and he can drive. The human driver doesn't have a problem. He can actually drive. But the steering system based on the camera cannot drive because the lane lines are not visible. Okay, so using the lane lines, you cannot find your position. You cannot drive by using the lane lines. Okay. We have collected data that shows that snow stays on the lane lines longer than in the lane interior. Okay. And there are also other situations where lane lines may not be available for steering control. So not only snow-covered roads, but also low-volume rural roads, including gravel roads. So low-volume rural roads, right? They may not have any lane lines. They may not even have a center line because these are low-volume, small roads, basically, right? So they may not have any lane lines. So you really cannot depend on lane lines to use your camera and drive. Also, some states have a lot of gravel roads. So in Minnesota, we have over 70,000 miles of gravel roads. 70,000 miles, okay? So gravel roads, absolutely no lane lines. There's other kinds of problems with gravel roads as well. Their quality will keep changing with time, and they have to be, they have to be cleaned up and, pressed every once in a while. So how do we drive on such types of roads? Now that is important because one of the applications that we will talk about for autonomous vehicles is actually rural environments. So in rural environments, you need, you might not have much public transit, right? If you have older people who are not able to drive and so on. If you have autonomous vehicles, that would be incredibly useful. But in rural environments, you also have a lot of gravel roads, you have low volume roads. So we could use, so that's why MnDOT funded this project for us. And what we are doing in our project is we are using high precision GPS, right? So regular GPS is normally accurate to about 1.8 meters, right? So GPS normally is not going to give you very accurate position. It's good enough for navigation. 1.8 meters, right? 6 feet is absolutely fine for navigation. By navigation, right? The system that tells you take a right now, take a left now, and so on, right? For that, 6 feet error is absolutely okay. But for steering control, you can't have a 6 feet error, okay, for doing feedback for your steering control, right? So you need centimeter level accuracy. So in Minnesota, that we have a system called min course. Okay, so everything in Minnesota is called min something, min cab or min course. So min course is this is basically a correction system, RTK correction system, right? So there is at a few locations all around the state, there are basically stations which are very precisely known. Their location is extremely precisely known. And so receivers at those locations receive GPS signals, and then they calculate the error in the GPS signal and they transmit the errors. And so in your car, you can receive those correction signals. And so you can improve the accuracy of your GNSS by using those correction signals. So those are called RTK corrections. And so we have some of this min course supposedly works all over the state. Okay. And so that's what we're trying to use for our driving. Okay, for our driving of the min cab vehicle. Okay, so how well is min course going to work? How accurately can you find your position and can you do steering control, right? Using GNSS. That is the question. So basically, it turns out that in rural environments, so this is the rural, this is this is the rural road. So here you can see that you get more than 20 satellites all the time. So on a rural road, you have clear visibility to the sky, right? You have good visibility to the satellites, and you can see all the satellites. You're more than 20 satellites are visible here all the time. Okay, so you're going to get pretty good GPS measurement over here. But if you look at downtown out of 14 minutes or so of driving, for 4 minutes there was absolutely no signal. So downtown you have all these tall buildings, right? So you might not have any GPS at all for a significant portion of the flight. Okay, and sometimes you have very few satellites available. Sometimes you have none. Sometimes you have very few. Local roads, basically suburban roads, you can again have some pretty good satellite visibility. But if you have local roads with trees, then you can lose visibility to the satellite sometimes as well. So that is another thing to keep in mind. So because of all these reasons, what we need to do is we need to do sensor fusion. We need to combine IMU signals with RTK-corrected GNSS, and then we need to use estimates from those algorithms for our steering control. Okay, so basically what I'm trying to tell you is you cannot entirely depend on just receiving GNSS and RTK corrections. Okay, so you need to use some good estimation algorithms combined with IMU so that you can you get fast and reliable updates of your position. Because if you don't know your position, you cannot do steering control. Okay. So that is one thing, that is the other thing that we have worked on, and what I'm going to show you now is this autonomous steering on energy powered drive. Okay, so this is the road which has some pretty sharp curves, okay? And what I'm going to show you is this video in which we are using RTK-corrected GNSS and estimation algorithms, and we are doing steering control. So the driver is driving currently. Okay, so now he switched on the autonomous system, and so now the autonomous system is driving. And the system does a pretty good job. So you can go around some pretty sharp curves without a problem. So this is a system that we have developed and implemented on the car. It's basically a feedback plus feed forward control. So you need a feed forward term for going around sharp curves. For going on straight roads, you only need the feedback term. So that gives you an idea. So it works pretty well. The good thing about this system is that we can do this demo quite easily on almost any road. So if we need to show autonomous driving on a new road, we can take the car there. Then we have the human driver drive first, and we use that as a reference trajectory. And then the autonomous system uses the human driver's trajectory as a reference trajectory, and we follow that trajectory. So it's pretty easy to set it up and do a demo at any station. So here you can see what the performance is in terms of lateral position error. So this is basically how much error we get with respect to the desired trajectory. And here you can see that the error is of the order of 10 centimeters at most. Okay. So this is during the very sharp turn at the end that you get a 10 centimeter error. Otherwise, the error is less than that. Okay. So this is about 90 minutes of driving over here. The azimuth angle error is very small. It's sub 1 degree, as you can see. So that is basically the orientation angle. Okay. So so that is so I'm moving on now to the next one. Okay. So these are all projects that have used estimation algorithms, right? For enabling some interesting autonomous driving ideas applications. Okay. So now I'll talk about a different application now, in which we've used estimation algorithms again. Okay, and this is on wake surfing boats and off-road vehicles. Okay. So this is an entrepreneurship related project. It's funded by a NSF-PFITT grant. Okay, so what we're doing in this project, right, is we are finding the position of the piston inside this actuator. So this is the piston cylinder actuator, right? So the piston is going to move back and forth inside this actuator, and we want to find the position of the piston. So such actuators are used, for example, on construction vehicles. So you can see construction vehicles here. You can see the actuator here, right? So this actuator is used to move the end effector. So the end effector is basically this tool here, right? So it's a bucket or a tool. And so these actuators are used to move the bucket, right? So the operator inside the construction vehicle is moving the end effector, okay? So what is the advantage of measuring the position of the piston inside the actuator? It helps us know where the end effector is. Okay. Why do you need to know where the end effector is? Because it helps you do all kinds of automation. So there's all these construction companies and agricultural companies, right? They're interested in introducing all kinds of automation on their vehicles. So for example, if you want to dig right next to a wall, right? You don't want to hit the wall, right? You want to dig right next to the wall without hitting the wall. So then the vehicle can provide a virtual wall for you so that you never hit the wall, right? So you need to know the exact position of the end effector so that you can implement a virtual wall. Likewise, you can automate a lot of operations, right? So the operator can, pick up the soil and then he can show where the soil needs to be dumped. And then once he does that, the automated system can just keep doing it, right? He can pick up the soil and then it can go and dump the soil, right? So all kinds of automation can be implemented on these vehicles. And so that is why there are all these companies are very interested in finding the end effector position, which you can calculate if you knew where the piston was inside this, right? So what we have done is we have developed a magnetic sensor board using which we can find the position of the piston. So we model how the magnetic field of this magnet, how that varies as a function of position. And then we use that together with estimation algorithms to find the position. Okay. Now the advantages of this type of system are that magnetic sensors are very inexpensive. Okay. They can, depending on what sensor you buy, it could be $1 a sensor. Okay. So what we are doing is we are competing with other sensors like LVDTs and potentiometers. Okay. Millions of linear actuators are sold every year for ag vehicles, agricultural vehicles, construction vehicles, manufacturing, wake surfing boards, and so on. Okay, so the market for actuators and the need for position sensors on them is actually pretty big. Okay. So typically the magnetic sensor that is located outside the actuator, right, is a 3-axis sensor. So it actually gives you magnetic fields along 3 axes, X, Y, and Z. Okay. So this is one of the magnetic fields that I'm showing you here. Okay. And you can see it is pretty nonlinear. So the magnetic field varies as a function of position, and the variation is quite nonlinear, right? So normally magnetic sensors like Hall effect sensors, right? They are only used for detecting proximity. So you can use them, for example, to see if the actuator has reached the end of stroke. Okay, it's just a proximity sensor. But if you actually want to measure position throughout the stroke, then you need to use the magnetic field as, you can't just use a threshold. You need to actually model the magnetic field as a function of position and then use that. Okay. So this is what we do here. We use this model, and then we divide the region into 3 regions which are monotonic. Okay. So otherwise, this is a non-monotonic function, and then we use a nonlinear observer design method that relies on the nonlinearity being monotonic. So we essentially have 3 different observer gains for these 3 different regions. Okay. So this is a prototype sensor that we made in my lab here that you can see over here. Okay. So this is the microprocessor. It's a PIC microprocessor. On the back side of this board are the magnetic sensors themselves. Okay. What I'm going to show you next is a video in which this is a 10 centimeter stroke actuator. Okay. So if you want to measure the position of the piston on this actuator and you want to use an LVDT, the LVDT needs to be connected to the piston. So what we did is we put a plate at the end of the piston rod, and then we connected the LVDT rod to the plate. And so then as the piston moves back and forth, this rod moves in and out of the LVDT. Now the LVDT is a really good sensor. It can give you 0.1 mm accuracy, okay? But it is $400. That's one thing. Plus it needs to be physically connected to the piston. Our sensor, on the other hand, is a $50 sensor. It doesn't need to be connected. You just put it on the outside. No connection, right? It's a non-contacted sensor. Okay. So our company is called Innotronics, our startup company. And this video here, oops. I think I need to click on the video. Okay. So what you can see here, this is the actuator, and this is the real position that you can see in the ruler. And here you can see our estimates and the LVDT sensor readings. You can see that our estimates and the LVDT sensor readings are kind of on top of each other. Yeah, so you can also have high bandwidth motion, fast motion, and you can still track the position quite well. Okay. Yeah, so typically for this 10 centimeter stroke length, we get less than 1% error, we get 1 mm, less than 1 mm error, as you can see over here. So this is the estimate versus the LVDT reading, and you can see that the magnetic sensor follows the LVDT sensor quite well. Okay. So what we are working on now is we're trying to, so we have this new NSF PFITT project. We're trying to make this technology work better for long stroke actuators. So because this was a small stroke actuator, 10 centimeter stroke, right? You can imagine on a construction vehicle, they're going to have like, 70, 80 centimeters, one meter kind of stroke. So it has to work over a very long stroke. So that's what we're working on now. And so this is, this is a test rig we have in our lab. This is basically a thick walled cylinder with a long stroke. There is a motor and a winch that we have for moving this up and down, and then we can put magnetic sensors on it and do estimation. Yeah. So this is what we are working on. So there are a lot of applications for these actuators, like I told you, so this is called a planter. This is an agricultural vehicle called a planter, in which they have 30 actuators. So they actually have 30 actuators at the same time, and you're, seeding the soil. All the 30 actuators, right? They put, they're being used simultaneously, and such actuators are used in all kinds of oil rig applications, and so on. Okay. So we established this company in 2015, basically, and we are selling currently over 11,000 sensors a year. Okay, we had a slight hiccup last year where they ran into some problems, and so those problems have been fixed, and so we are hoping that the sensor sales take off some more. But basically, right now, the sensor, we have mostly one customer for the sensor. It's boat manufacturer Mastercraft, and so they use actuators behind the boat for doing wake surfing and wakeboarding. So they customize the waves behind the boat by using an actuator. And so our sensors are being used on those actuators for measuring position. So currently we only have one customer, okay? But we are, selling quite a few sensors to that customer. And if our sensors become more reliable in the future, right, if they can work for longer stroke actuators, then we might be able to find more customers in the future. Yeah. Okay. So let's see. We have 6 more minutes. Okay. So what I'll do is I'll talk about one more application. Okay. So, the common theme among for everything that I've talked about here is use of estimation algorithms. Okay, so that is the one common thing. That's essentially what my lab works on. Okay. 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 So we worked on protecting vulnerable road users like bicyclists and e-scooter riders, right? So what we want to do is we want to instrument the bicycle with low cost sensors. We want to track all the vehicles near the bicycle. And we want to predict the trajectories of all the nearby vehicles. And if any of the cars is going to pose a danger to the bicycle, if there is a danger of a collision with the bicycle, then we sound a loud horn. So the bicycle has a loudspeaker. We sound a loud horn. We warn the car driver to make the car driver aware of the presence of the bicycle. Okay, so that they see the bicycle and they avoid hitting the bicycle. Okay. Yeah. So basically, our cost target is $500. The total cost of all the components of the bicycle, sensors and so on, should be $500 or less, okay? So one of the systems that we have developed, and I'll just show you this one particular system, is essentially $100 sensor, right? It's a single beam laser sensor. It's got a pretty good range. In terms of range, it is pretty good. But it's a very thin beam sensor, okay? So it doesn't have a wide aperture, right? So you don't have a wide field of view. It's a very thin beam. It's $100, so that's pretty good. It's a pretty good sensor. What we do is we mount it on a motor, okay, and then we control the orientation. We basically do orientation control with the motor, and so that we can follow any car behind the bicycle. So this is the bicycle, right? And if the car behind the bicycle moves, whether it moves laterally or longitudinally, because we have a very thin beam laser sensor, we need to control the orientation of the laser sensor so that we follow the car. Okay. Okay. So, yeah, we use receding horizon optimization for doing the orientation control. We use, estimation algorithms. Okay. So what I'm going to show you here is this video. Okay, so this video is using an e-scooter. Okay, so what you see here is the e-scooter. On the back of the e-scooter is the laser sensor mounted on a motor. Okay, and then this car is going to come straight at the e-scooter, and then this sensor will track the car. And then, when it senses that the e-scooter is in danger, it will sound a loud horn. Okay, to warn the car. Okay. Not sure if the video will play right here. Oh. I have to do that again. Okay, so if I play this video here, you can see the car is coming straight at the scooter. This scooter sounds an alarm, and then the car moves away. And here you can see the motor control for tracking the car with the laser sensor. Okay, so I have a whole bunch of videos of this kind here. So here you can see the car behind the e-scooter doing some kind of a weaving motion. Yeah, so we have a, we have a bunch of videos, okay, and you can, what we are trying to show you here is no matter what the car behind the e-scooter does, it can have a weaving motion, it can make sudden turns and so on, but in all cases, we are actually able to track the car by doing orientation control of the motor. And so we are able to track the car behind the e-scooter and provide a warning. Okay. One other interesting work on this system is one interesting work that we have done is combined a camera with an RP Lidar. Okay, so with the RP Lidar, which is a 2D Lidar, it's a low cost Lidar, but we don't, first of all, it is low density. We don't get much measurements from the Lidar. Secondly, we don't know where the measurements are from. Is the measurement from the side of the car, or is it from the front of the car? Is it the lateral distance to the car, or is it longitudinal distance? We don't know those things. So it's very difficult to use the RP Lidar measurement. So what we do is we combine the RP Lidar signals with the camera, and what the camera does is it basically draws a box around the front of the car and the side of the car. So we're able to find out, which portion of the image is the front and which portion of the image is the side of the car. And then we, by projecting the Lidar points, we know whether the Lidar reading is from the front or is it from the side. So that gives you information about what is the lateral distance to the car, what is the longitudinal distance to the car. So you're able to utilize the information from the RP Lidar. Okay. So here you can see that, we can detect the front and the side, and we can, you know, you can see where the RP LiDAR points are being projected to. Is it the front or the side, essentially? So, yeah, so we are basically able to fuse the camera and the 2D LiDAR and get, we are able to estimate the distance to the right front corner of the car, so the distance to the right front corner gives you both the lateral and the longitudinal distance. So that is really what we want to do. Okay. Okay. So, we have other devices that we make for protecting construction zones and so on. So these are some examples of devices that we have built in my lab. This is a smart traffic signal. It's remote controlled, and it's got sensors on it to track vehicles correctly. So these are, these are other devices that we've made in my lab. These are various kinds of devices for protecting construction zones on roads. So we can detect if a car is going to intrude into the construction zone, and we can provide warnings and try to prevent intrusions. So this is a very small portable sensor. This is kind of a more heavier, big sensor. Yeah, so that kind of gives you an idea of various, transportation related projects that are going on in my lab. They're all related to estimation algorithms, essentially. These are some of the people that we are working with. So Lee Alexander has been in my lab for 15 plus years, so he's been there for a long time. A lot of the others are PhD students. So with that, I'll stop my presentation.
Let's thank Professor. And anyone have questions?
I have a question. So you talked about integrating IMU and RTK GPS. I wanted to ask if you could tell us more about that. Would it be helpful to consider integrating other sensors as well, like radar, together with that to improve the estimation? And do you do a nonlinear observer design for the localization in that case? And maybe, complicated question, but also I suppose there's some parameters like the tire slip you mentioned in the beginning. Do you also estimate that in some way as you're trying?
Yeah. So we need, we especially use that slip angle for tracking other cars on the road. So we estimate and use that in some of our projects. One of the projects I didn't show you is we have a system on the back of a snowplow for tracking vehicles near the snowplow. So that is the system where we use the slip angle estimation. Okay, so to answer your question about can we use other sensors for localization, right? You can try to use other sensors. So besides the RTK, GNSS, and IMU, you can use, for example, people have tried to use LiDAR. Now, in some environments, rural environments and so on, there might not be much features around you that you can add, that you can detect with the LiDAR and then use it, so unless you have some recognizable features like, say, traffic lights, stop signs, or something, you might not really be able to have a database of known objects that you can use together with LiDAR. So in rural environments, that sometimes becomes a challenge. It's easier in urban environments to use LiDAR. So radar sometimes, you can use radar to find slip angle as well. So there are a lot of stationary objects around you, right? So you don't need to know what that stationary object is. You can get a reflection from a stationary object from your radar. And as long as you know it is a stationary object, you can actually find your slip angle because you get the radial velocity And so you can find the components of the velocity, and if you have at least two stationary objects, it turns out you can calculate a slip angle. So yeah, you can try to use some other sensors to help your localization task.
Other questions? I have one.
Yeah.
A little bit maybe more a higher level philosophical related to the predictive display. So you address the fact that like you account, say, for kind of difficulty, maybe like a sharp turn by having additional images. So more than the field of view you showed, you are sensing, right?
Yeah.
And I thought that the same thing could be applied in general in teleoperation, where, of course, we can recreate the car windshield that we kind of experience from the driver's seat. But with sensing, we have the ability to collect additional data. So do you imagine an advantage to exposing that information? Like, for example, I don't know if you do this or not, but using those side-facing cameras, you can improve the interpolations significantly. And like, it was very clear in the video that it was very accurate and really responsive. Is there anything else you could do with those camera images? Because it's a lot of data to collect to then just use for, let's so to speak, corner cases of interpolation.
Yeah, I mean, the more cameras that you're trying to transmit over a wireless network, right? The more difficulties you're creating, because you're going to get more latency. So yeah, having to use not only the center camera but the side camera, yeah, it's going to give you more latency. What are the other applications?
Like, for example,
I mean, it's we haven't done intensive work really in these. And there's many aspects to this teleoperation system. Essentially, so as a human driver, maybe you don't always look only straight, right? Maybe sometimes you need to look this way, that way, right? Depending on what is going on. So the other cameras would potentially be useful to the teleoperator. But we haven't really looked into what are those cases? Are there, when do we need to, what do we need to transmit when, and what do we need to use? And then in the longer run, there is also there's some automated monitoring needed as well, in the sense that what would be good to do is each teleoperator might monitor multiple vehicles at the same time, because you'll be sitting in a room in which there's 10 cars that you're monitoring, and most of the time you don't need to do anything. The 10 cars are autonomous; they are driving themselves. You don't really have to do anything. But occasionally, one of the cars needs help, needs intervention, and then so maybe the system needs to notify you that you need to look at this particular car and you need to do something, right? So there's potentially some automated monitoring and those kinds of things that can come into the picture as well. So we haven't really studied these kinds of problems yet. There's a whole bunch of problems.
Yeah, that was exactly, I think, what I was getting at, is that, for example, you could use your method in some feedback loop to trigger, hey, maybe it's important that I expose a wider field of view in this critical moment to the teleoperators.
True.
Anyway,
Yeah. So even something like, okay, you detect the fact that you're turning, and so you need to show the side camera now.
Cool. All right.
There's one
Yeah,
question.
I think
I'm curious for the magnetic sensor. Could you give us a sense of what the main challenge is when you scale the size? You mentioned that it's still, is it that the magnetic field, the nonlinear function starts to look different, or?
Well, there's actually multiple challenges. I'll tell you what the biggest challenge is. So the easy challenge is the fact that you need to use multiple sensors. So right now we can just use one sensor board, and that is enough, for up to 15 centimeters of stroke. So I showed you a 10 centimeter stroke actuator, but up to 15 centimeters, one sensor is enough. But when you start going to much longer strokes, right, you need to use like 3 sensor boards instead of 1 sensor to cover the entire stroke. So that is one thing. Now that's not such a big deal by itself, but the other problem that happens is that, in the case of ferrous actuators, you get a lot of hysteresis. Because this actuator, the one that is being used on the boat application, is an aluminum actuator. It's not a ferrous actuator. In the case of ferrous actuators, as the magnet moves back and forth, the cylinder gets magnetized and demagnetized by the moving of the magnet. And so you get a lot of hysteresis. And so that hysteresis is very difficult to compensate for. It's very difficult to model, and then to compensate for that hysteresis is not easy. So that is one of the biggest problems we have.
Nice. All right, let's thank Professor again.